All right, we are live. Welcome everyone to another Perl Mongers Night. I was just saying before how it's awesome to have the regulars come to these meetups because I don't know what I would do if you guys didn't keep showing up. So thank you so much. Martin, you're laughing, but you know you're one of them. Ken, Gabriel, Aaron's now a regular. Thanks, thanks so much for coming. Tonight we have a special guest all the way from Madison who's going to show what he spends his free time doing, which is mind-boggling to me because I don't understand half the stuff that he's going to be talking about. But Timm Murray from Madison is going to show us how he got his quadcopter to run on Perl and all the fun stuff that goes along with that. So thank you so much, Tim, for coming. The show is yours. Here we go.
All right, let me just put up my screen here. Where's the start thing for? Oh, that's the one.
All right, give a thumbs up again if you can hear.
All right, can you hear me?
Yes.
All right. All right, so programming quadcopters, part 1 and 2/3. So part 1 was supposed to be the presentation I gave at Mad Bongers about 2 months ago. And when I had intended that one to be for people who maybe didn't know a lot about Perl or programming in general, but wanted to see like quadcopters in action. So it was a little thin on programming and was more focused on the quadcopter side of things. And then I intended that this would be part 2, which would be more programming centric. But then I went back and looked at the video I had recorded of part 1, and it was terrible. The angle was too wide, you could barely hear me, you couldn't see the slides at all. So instead I kind of rejiggered part 1 entirely to just have a little bit more programming involved, but still kind of centered on the quadcopter side of things rather than Perl. So just a quick overview of the system. UAV Pilot is the library up on CPAN that I created. And it's a library for generally controlling drones. So not just any one thing, like Node.js has Nodecopter, which works just on the AR drone. I didn't want to limit myself to just that. So it has kind of a modular system where you can put in plugins and build it for any other kind of drone, just like DVI has different database drivers for MySQL and PostgreSQL and so on. So I did start with the Parrot AR drone, which was a very good way to get started. I kind of got away from the Parrot in general, and I always wanted to do more of a custom quadcopter. And it also has this unified API so that if you have video implemented on one, you can use a lot of that code for the other, because decoding H.264 is about the same on anything. So a lot of different systems will broadcast H.264. So as long as you have the decoder for that, it'll work. Same thing for joysticks. So the quick and dirty look at flight. You have roll, pitch, and yaw. Roll, I should bring up one of my quadcopters. Roll, this is the front of it going out. Roll is going to be like this. Yaw will be like this. And then pitch will be up and down. Now, in an airplane, moves a little differently. So if you put thrust on an airplane, it's going to go forward faster. If you put thrust on a quadcopter or a helicopter, it's going to go up faster. To go forward, you have to pitch forward on a helicopter, and that will push it along. So that's something you actually have to keep in mind when designing the library and making your calls, is how you go forward is going to be different between these different systems. So this is a typical setup of how a racing quad like this one is going to work. And I don't think you guys on the meetups group can actually see this. I'm sorry, but anyways, so you have different components inside the quadcopter that are all, you can kind of buy them all separately. But you have the video transmitter that just gets data from the video camera, and that just sends it out over the air. And then, oh yes, this slide was messed up. There, flight controller. So the receiver puts data into the flight controller, and the flight controller gives data out to the motor controllers, and then that goes from the motors to there. And you'll notice the video transmitter and camera don't connect to the flight controller in any way, at least not in this simple setup. The only connection between them is the battery. And the flight controller is not terribly necessary on airplanes. Not so much on a lot of the helicopters, but it is very necessary on quadcopters. And the reason for that is that to control how a quadcopter moves, you have to make independent adjustments to all four motors. It's almost impossible for a human to do that, no matter how good of a pilot you are. And it has to be constantly making those very tiny adjustments to keep it stable. It's not inherently stable that way. So the flight controller is what enables you to do that.
The velocity you're controlling? What are you controlling?
You're giving it instructions of, I want to yaw, pitch, and roll, and thrust, and then it works out what that means.
But the motors themselves, all you really have is how fast they're going, right?
Not even that. The flight controller takes care of all that.
Right. Okay.
Yeah. So I want to make a Raspberry Pi do this. And a Raspberry Pi has a very nice camera module installed. So it can take over the stuff in the red block here. I think I messed up this slide again with the flight controller. Yeah, it's supposed to be still there. Anyway, so the parts marked in red are all stuff that a Raspberry Pi can do. It can give instructions to the flight controller, and it can take the data off the video camera and then send those out over Wi-Fi. So this was my plan for creating a Perl-based quadcopter. Now the other thing I wanted is to change how things are controlled. So historically, going back to all the old RC airplanes, everybody would use a controller kind of like this one. And this works fine, you know, the two sticks thing. This does throttle, that's yaw, and this is pitch and roll. And this has served the RC community very well for a couple decades now. The thing is, a lot of the other things you'll see out there don't really use something like this. They use a joystick. Notice the Apache helicopter here. That has a joystick. The one on the left there is the Predator drone setup that the military made. That's joysticks. The only real exception to this on the right is this little rover here was meant for anti-sniper work, and they just straight up use an Xbox controller. I figure the kids coming out of into the Army these days, that's what they know, so, and it works just fine, so why change it? So that's the only real exception there. But I didn't grow up with an Xbox, I grew up with TIE Fighter, so I'm really used to a joystick like this one. And that's what I wanted to use. And doing this with Perl meant that I could take in instructions from the joystick directly and then send them to the quadcopter instead of just relying on the other radio links. Now, if you've never worked with Raspberry Pis before, just a single board computer, it's real small. And this is actually one of the new Model 3s. This is the first one that has Wi-Fi on board. Otherwise, you had to have a USB dongle. So it's a single board computer. Pretty much everything you need to run a computer is on here except power. There's several models. I have the Model Pi 2 on this quadcopter, and that's a quad-core CPU on there. And you'll notice it has this pin header on the side here, which can provide just GPIO, which is just on and off. But there's also a serial link. There's other kind of data links like SPI and I2C. We don't really need to go into those too much, but if you've ever want to work this seriously, you'll probably run into those. And it all just runs off a micro SD card on the back here, which is not exactly fast, but it works out. One thing to note about the Raspberry Pi, it's not a real-time system at all. You're going to be putting Linux on here, which makes it very flexible. But if you think about how a quadcopter works, if it needs to make those small adjustments to those motors on the fly, it can't wait to do that while writing a log file out. Everything has to happen when it needs to happen. So Raspberry Pi, at least when it's running Linux, there are other alternatives out there, but if you're running Linux on it, this wouldn't be suitable as a flight controller on its own. So it's also got the camera connector. When I originally wrote this talk, I think the Pi 3 wasn't out yet, but now it is, and it has Wi-Fi on board. I would still probably ignore that because it does not have an external antenna adapter. And if you're flying around a soccer field about 100 yards out, it's probably not going to get good signal that far out. So I would still use a USB Wi-Fi adapter with an external antenna. The Pi Zero, if you can actually find one, is very cheap. It does not have a camera connector. So that would still be able to work with Wi-Fi and everything if you just wanted to control and fly it around. But it's not going to have the video streaming by itself. So on board a flight controller is, it's kind of hard to see, but it's right in there. On board there is an accelerometer and a gyroscope, and possibly some other sensors. Sometimes a barometer is used for altitude or GPS as well. But generally you have an accelerometer and gyro at a bare minimum, and that's what allows it to sense how it's moving and keeping it in stable flight. So its job is to take those instructions from the radio receiver and then translate those into the motor controllers. A lot of times there are compatibility modes that will run things like helicopters and planes, which in those applications usually it's making things easier to fly for new people. I think a lot of the more serious flyers would absolutely hate to use a flight controller on it. They have no need for it at all. For quadcopters, it is absolutely necessary. And there's quite a few models then. It seems like they're coming out with a new model every week. The Naze 32 is the one I really like. I've experimented a little bit with some of the others, but the Naze 32 costs about $25 and it works for everything I need, and I haven't yet had a reason to branch out. So you generally work this out through the Naze 32 and usually any of the other open source ones out there. It's done through this CleanFlight program, and it's actually a Chrome browser app. And this will load the firmware right onto the Naze 32, and it's connected over USB here, and you can see as I move the quadcopter around, it's figuring out with the gyro and the accelerometer how it's oriented. And it has all sorts of other settings in here. Ports, I'm going to be using a serial connection to actually tell it all the movement commands. So that's configured in here, and that's configured in here. Down here at Spektrum, we'll talk a little bit about that a little bit later. And this shows you the motor counts and all the motor, the propellers on this counter-rotate with each other so that their effect of gyroscopic effect will be canceled out. And that's also how it does yaw control. It just speeds up one motor and slows down the others, and that's what makes it spin. So a few other settings in here. PIDs are very important. I like to use the analogy of an oven. And if you thought about how you want to get an oven up to a specific temperature, and you've just got a button there that can turn on the heating element. So you say, okay, I want this up to 350 degrees. I'm just going to sit on this button until it gets to 350 degrees. Okay, it's there now. I'm going to let off. But that heating element's still very, very hot. And the heat is going to keep going well past 350 degrees. And now you've burnt whatever you got in there. So next time you get a little bit smarter and you pulse the button until it gets up there, and then it just kind of waves around that 350 degrees real nicely. And that's what PID controller does. It's 3 different numbers that you have to tune that tell it how to kind of pulse that button. And that's actually how the flight controller controls the motor speeds. Then here, if I had this receiver set up, you would be able to see how the roll, pitch, and yaw commands are all coming through. And I think that's most of the most important things. There's no GPS on this one. And motors, I can actually set these. I don't have a battery connected to this right now, but you could actually manually set each motor for testing purposes. So that's most of clean flight for you. So getting back here, how do we control all this? So these top ones, the joystick goes to computer, goes to Wi-Fi. All that's going to be kind of on your laptop or whatever out in the field. Then for Wi-Fi, there's this protocol I just invented, Wumpus protocol, because I like doing Wumpus branded type things. And that just goes to the Raspberry Pi that's on board. And then that's going to go to the flight controller over the Spektrum protocol. And that's a specific company that kind of put out these type of receivers. And we'll kind of go into the details of that in a little bit.
You said that you're doing that over a serial port?
Mm-hmm. So this is the old-fashioned way to do it. This is how RC cars and planes and everything have communicated with servos since forever. You've got this pulse that there's 20 milliseconds in between them. And if the pulse goes high for 1500 milliseconds, that is the middle position on a servo. So if you think of a RC car turning its wheels, when it's centered, it'll be at 1500 microseconds for that pulse width. At 2000, it's going to be 90 degrees to the right. At 1000, it's going to be 90 degrees to the left. And then everything in between. And then it just sends it over the wire every 20 milliseconds. You'll notice this is actually a little bit analog because you, of course, never get perfect square waves in real life. So this pulse width is kind of a guesswork sometimes. And also, there is a combined protocol where you only send this pulse over a single wire for multiple channels. But traditionally, these have been just one wire per channel. So it's a lot of wires to string around. So that's how it's been. And we don't necessarily use that specific signaling type in a lot of modern things, but you'll still see that language of microsecond length in a lot of the things going on here. So the Wumpus protocol, for example, here. Here you'll just get the packet factory, and we just want a radio output packet. And then we're setting what we want to encode that packet to. So here we're setting channel out. We don't want any pulse. Channel 2, we're just saying a pulse of 1000, so that's going to be 90 degrees to the left. And then this file handle we have here, we're just pretending that's our serial connection, and we're just writing out over that serial connection. And then on the other side, we also have this packet factory that will read in the buffer, and that's going to translate it back into a radio output packet, and from there we can send on the command to the flight controller. Okay, so in between your laptop or whatever you're bringing out in the field and the Raspberry Pi that's on board the quadcopter, this would be the Wumpus protocol. Very simple, just have magic number, your version number, and then packet count is very important because this is going to be over UDP. You are going to get packets out of order, and if it sees a packet count lower than the one then it's seen previously, it's just going to throw this packet out. That's just how you deal with things on UDP. Message ID, so that's the type of message. Sometimes you want a startup command, sometimes you want just an ACK, or you have that radio output, or there's some kinds of status packet, and the message ID just tells us that. Then the length and checksum for everything, to make sure everything's okay, and then the payload. Generally, we have about 16 bits per channel. So that's actually going quite a bit beyond that microsecond count we had before, ignoring kind of the analog factor there. So we'll have quite a bit more resolution on that, quite a bit more than we need, in fact. So the thing with pulse widths also is we don't want to be controlling them over the Raspberry Pi. If you remember when I said that the Raspberry Pi is not a real-time system, to make those pulse widths work, we would have to say, okay, we run our loop really hard, and we want to start a pulse width now, and then we wait exactly 1,500 microseconds and shut it back off again. Not only are we burning out a CPU doing that, we are also not so sure we're going to make that 1,500 microseconds. We could have our process completely suspended by the operating system, and that would be very bad. So we don't want to be using pulse width. Spektrum. Well, there's been all these serial protocols popping up over the last couple of years in the RC world, and Spektrum is one of them. And it's been made by a specific company, but people have reverse engineered it, so I just worked off what they did. And it works. It's just a binary serial protocol, 1,500 baud, which is more than enough speed for this. It could probably, I think I worked it out, it would go down to 24K, something like that. Would work just fine. But 1,500 baud is overkill, but it's, you know, whatever. Signal inverters. So there's this other one called S-Bus, where they actually inverted the serial protocol, so you need to invert the whole thing, and I didn't want to deal with that. So that's why I rejected S-Bus. There are a couple others out there, but Spektrum is just what I kind of worked for me. So I worked out the device Spektrum module. That's up on CPAN as well as its own thing. And then we just invented that Wumpus protocol between our Pi, the Raspberry Pi, and client. And you can see down here some example code of how we send from the Raspberry Pi that's on board the quadcopter going out to the flight controller. These numbers are, now I can't remember. Are they between 0 and 200? I don't know. Anyway. Doesn't really matter. So putting this all together, a lot of UAV pilot is based on any event. I've honestly kind of regretted that decision at this point, but it is what it is. So I wrapped it in this easy event, which is kind of somewhat wraps away some of the complexities of any event, because its API is a bit inside out, and easy event kind of abstracts that away. But the important thing here is you have a driver followed by a control. And the driver is very low level. You don't necessarily have commands like yaw, pitch, and roll. If you look at the AR drone one, it's things like ATREF. And you'd have no idea what that means unless you actually looked at the AR drone documentation. But that's okay because you don't actually touch that. You just pass that driver onto the control. And the control is the thing that has all the nice yaw, pitch, roll, throttle that you want to work with. And control event makes it a little easier because that goes into an event loop. Especially on the air drone, that was important because you have to send a new command every 20 milliseconds, or else it kind of forgets you're there. And so the event loop will handle that processing. You don't have to do it yourself. It's not quite so bad on the my custom quadcopter, but it would still be better if you kept it going all the time. And then just at the bottom, you just init the event loop and start any event on the condition variable running. Okay, so this is the server side, which is really the Raspberry Pi on board the quadcopter. And we have these different backends for the server. So we could put in SBus, the other one I was talking about that had the inverter. We could make an SBus backend if people wanted that. Could make any kind of serial bus they wanted. If somebody wanted even the pulse width, that could be done. All pluggable. But this one just does the Spektrum. We tell it what serial port we want, which AMA0 is actually a serial port that's on one of the pins on the Raspberry Pi rather than USB to serial adapter or something like that. We don't need to do that. And we just tell the server, listen on port 5000, and here's your backend to how we send commands, and then we start the listening loop there as well. Okay, so that's all the how we control the quadcopter. So let's talk about video. When you get a racing quad and want to do FPV video, you're going to be all excited. You'll open up your video transmitter documentation, and you'll see a table like this one that tells you all the frequencies that run for each channel on this receiver. So this one has 32 channels, so you can run 32 quadcopters at the same time, right? And have them all send video and it'll be all right? No. Those 4 are the ones you can use. Just like Wi-Fi, there's really only 3 Wi-Fi channels you can use without overlapping and stepping on your neighbors. These are the 4 you can use. If everybody's equipment works out, you can use 5. If you're a real tyrant and can tell people very specifically what equipment to use, I've heard it getting up to 8. But in general, if people are just bringing out whatever they got, these 4 are the ones you can use. So that's a huge limitation for racing. It means only 4 quadcopters can really be in the air at a time. We'd love to have races of 10, 15, 20 people. Right now, technically, it's not possible. So to do that, to get 10, 20, however many people going, we're going to need digital video. The first obvious choice is Wi-Fi with the Raspberry Pi camera. Raspberry Pi camera is very good. For $25, I believe it is, you will not find a USB camera better than this one. GStreamer is a very nice library. It uses kind of a pipe setup, because you're probably all familiar with Unix pipes of sending text data one into the other. GStreamer has the same idea built in for video. And then RTSP is just a streaming protocol, very good for live streaming. And we're going to use H.264, which is a very popular compression protocol. It's used for Blu-ray discs, I believe. And we're going to send every frame as a keyframe. Now, if you're not familiar with how video compression works, a keyframe is all the data, just like a JPEG. It's the complete description of an image. After that, you're going to get intermediary frames. And that just tells you the stuff that's different from the previous frame. So that can be encoded very slowly, very compactly with the right algorithm, because if you look at any given movie, there's probably not a lot, even in a big action film, there's not a lot that changes between each frame. But the downside of that is that if we drop a frame, it's going to mess up the image from then on until we get another keyframe. And so what I've done here is a little while back, an update was made to the Raspberry Pi's camera driver that you could specify when you get a keyframe. So I said, give me a keyframe every time. And it turns out the bandwidth on that is not too bad compared to what Wi-Fi can put out. So it actually works pretty well. And we only need a 640 by 480 image. And that's actually better than a lot of the headsets that are out there for the analog right now. The Fat Shark Dominator here, that's a $500 headset, and it's just getting up to 600 by 480. And the image quality looks terrible as well. It's sufficient for racing around. It's not something you want to broadcast. Most of the broadcasts of FPV racing on YouTube, people will put a separate action cam on board. That is not what they actually see while they're racing. Now, the one downside of digital video is latency. Analog video is instant all the time. Digital video inevitably is going to have some latency involved. So we need to keep an eye on that. And with testing, even with all the keyframes being sent and not too bad on the resolution, that's about 2,000 megabits per second, which isn't too bad for Wi-Fi. Even if you're at the far end of the field and not getting very good signal, you can still do about 2 megabits. There you go. Now this is the easy way just to set up a video server. So on the left here is the what you would run on the Raspberry Pi to send video. And we're just the GStreamer here. You can see the pipes on the exclamation points can be considered pipes from a Unix perspective. And so we just get it in from the Raspberry Pi camera driver. We give it a bit rate, and we just set the bit rate real high because we really don't care. It's actually going to be much lower than, I think that's 10 megabits, something like that. It's going to be much lower than that. And then we have to set a type. On that first line after, excuse me, first line there, you see the video XH264. People keep thinking that's a MIME type, but actually it's kind of an internal GStreamer thing. So this is called the caps or capabilities, and we're just saying that we want an H.264 stream with this width and height. And then we have to just have some boilerplate for parsing the H.264 frame in a queue. Sometimes with GStreamer, multimedia formats are very complicated. There's a million of them out there, and they all have their own weird thing. And sometimes with GStreamer, they just you have a pipeline that you think should work, and it's not. And you put in, oh, just put a H.264 parse in there or a queue or something like that, and it suddenly works. I don't know why. Half of this is voodoo to me, to be honest. But this pipeline all seemed to work. But then we're putting it into the RTPH, which is part of the streaming protocol, putting that payload on, and then eventually we get it to UDP, and we're sending it out to what's going to run on the right side here. And that's just setting up a UDP source, and then we're kind of undoing everything and then showing it on the screen using the auto video sync. The nice thing about the auto video sync is if you're running on Linux or Mac or Windows, auto video sync kind of works out how to display the video. So how bad is the latency? Well, without too much tweaking, just kind of doing what I had up there before, I pointed the camera back at my own laptop screen while a stopwatch program was running. And so you can see the latency on the screen here, and it works out to about 100 milliseconds, which isn't too bad. So if you think about this is 30 frames per second. That's about 33 milliseconds per frame. So this is about 3 frames behind what the camera is actually seeing. I'd like to get that down to 2, but I don't know if that's possible. 1 is probably not possible without some very specific hardware, maybe FPGAs, crap like that. That would have to be a little bit exotic. But I think 2 might be doable with tweaking. I don't know. We'll see. Now, all of that was on just the command line, no Perl involved. But we can use GStreamer in Perl with the GStreamer 1 library. And that would give us the ability, if we can work it all out, because GStreamer is also very complicated, of doing on-screen display. So things like what's your battery level at, or what's your altitude, what's your orientation. All this should be possible, but it kind of has to be worked out. Well, is Wi-Fi a good enough connection for this? Plenty of bandwidth. Not worried about that. Even if you have 10 people on the same channel, plenty of bandwidth. No problem. Latency, not bad. Could be better. We can probably work it out. For cost, dirt cheap, no big deal. Weight's a little high compared to some of the micro cameras and transmitters that are out there right now. But I've weighed between the two I've got here, my racing kit versus my Raspberry Pi setup. And the Raspberry Pi setup is about 100 grams heavier, I believe. And it's got much bigger motors, so a lot of that factors in there. And I could probably shave off some of the weight on the frame there as well. Now, what about distance? A lot of times with FPV racing, we are racing on soccer fields or forests. And is Wi-Fi going to be good enough for that kind of environment? Well, for starters, everything else being equal, a lower frequency is going to travel further. So the video cameras normally that have been on the analog frequencies so far are 5.8 gigahertz, which is rather high. 2.4 gigahertz on Wi-Fi, even old-fashioned Wi-Fi, that's a smaller frequency, so it's actually better in this case. And since we're flying mostly out at soccer fields and forests, there's not much interference on 2.4 gigahertz out there. There's probably nobody else using Wi-Fi. There's nobody turning on their microwave. So actually 2.4 gigahertz is kind of a good frequency.
How much farther are we talking?
That hasn't been, I haven't tested yet, but I think all else being equal in terms of signal strength and the antenna, it maybe you'll get a extra soccer field out of it, or more importantly, you'll be able to punch through trees easier. Yeah. Okay. One thing we have to keep in mind. Sometimes your signal drops out on your Wi-Fi, and you might notice on your, whenever you're looking at the data on that, your signal drops, it renegotiates to a different speed. You probably didn't even notice it doing that. It might have lagged out a web page for an extra second. Probably no big deal. When we're running quadcopters, it's a very big deal. Because we're sending movement commands constantly, those extra seconds are very, very bad. So to fix that, we can actually force a speed. If we go down to 24 megabits on modern Wi-Fi, that's plenty of bandwidth. We don't need more than that. 11 megabits would be enough. So let's just use that. Now, when things get really serious, there's something called Wi-Fi broadcast. So in standard Wi-Fi, when you're connecting to an access point, there's a lot of communication going on in between there. And that means that every packet has to be ACKed between you and the Wi-Fi access point. And what's more, if it's encrypted, you have to send it to the access point, and then it sends it out to each client that's the actual destination. So there's a lot of round tripping there. Whereas with Wi-Fi broadcast, you're just directly injecting frames into the Wi-Fi USB, and then there's no association or anything. It just sends it out there just the way TV broadcast would do. And whoever's out there that can pick it up is whoever's out there that can pick it up. So that's probably where things will need to go with this. Talk about polarization a little bit. So if you ever went out to a, let me see if I can find, I left it over there. If you ever went out to an FPV event for racing, you might have seen those funny little antennas like this. They're kind of a clover leaf shape for those of you who can't see it. And I'm kind of wondering what's that all about. Sometimes you see it in plastic covers like this one, but generally you see them Well, you might see either one of those. These are for 5.8 gigahertz. This is for 2.4 of Wi-Fi. That's why it's a little bigger. It has to have a longer wavelength. But generally, you don't see just your simple monopole antenna. And the reason for that is polarization. All those, and that has to do with which direction the wave is waving. So in a monopole antenna, it's just waving in kind of one single plane. And if you think about a quadcopter going hard around a bank, it's going to mess up the polarization. So wherever your base station is and wherever your quadcopter is doing, you're going to lose signal because of that. With circular polarization, it's kind of in a big sphere, and it will line up no matter how the two stations are oriented to each other. So that's why you see these funny little cloverleaf antennas. And we have to do the same thing with Wi-Fi, which is no big deal because fortunately they sell 2.4 gigahertz cloverleafs, and we can just pretty much use the same thing with the SMA connectors, as long as the dongle has an external antenna adapter. So, talking about the chassis here. So I didn't just want to do the programming of Perl with the Raspberry Pi. I also wanted to make my own chassis. So I made this out of cardboard. It's laser cut. And it's coated in paraffin wax, which was designed so that it makes it much stiffer. You won't be able to bend this quite as easily as just straight cardboard. And it also makes it waterproof. I did later find a flaw in this plan. I left this in my car on a hot day, and half the paraffin wax melted off. But cardboard is lightweight and strong. A lot of the really expensive carbon fiber frames, for the same size, this is just about as light as any of them, and this cost me, well, the Badri, the makerspace I belong to in Madison, charges $10 an hour for laser cutter time, and this I cut this in a half hour, plus a bunch of used Amazon Prime boxes. Oh no, this was an IKEA box actually. I had very nice big pieces from IKEA. So very cheap and very lightweight, but we do have to work this out in SVG to make our design. So SVG is something we can do in Perl. Here's your first big problem, though, is how do you get consistent dimensions in SVG? This turns out to be a rather difficult problem because if you look through the SVG standard, you'll eventually find this little paragraph. And basically what this saying is SVG uses px as the default unit. Now, how big is a px? Well, that depends on the environment. If you transfer your SVG from your laptop that maybe has a 1080p screen and you transfer it to a desktop that has a 4K screen, the definition of px has changed. And so how many px's there are in a millimeter has changed. And so one of the problems I found is that when you convert on one computer, you have to make sure you actually do the laser cutter with that computer. Because if you convert it, copy it to the other computer that's already on the laser cutter, that's set up to run it and everything, if you just copy it over, the dimensions are going to be off. This is greatly simplifying everything, by the way. SVG is terribly complicated, and I don't want to deal with it anymore, but I have to. So anyway, the most consistent way I found to do this was to set up a view box. So here I'm saying I want a width and height of 500 millimeters, and I set up this view box that every coordinate I enter will be related within this view box. So it's just 0 to 500, and I can just say any coordinate between 0 and 500, and it will work that out, and it will line up with the millimeters. And as long as I convert it on the right computer, it should all come out correctly. And then I just go through a little bit of the frame construction. On the left there, you can see the laser cutter running it off the cardboard. I made 2 layers at a time and just glued them together, just your standard white Elmer's glue. And then I just found ancient computer manuals to weigh them all down. And then laying them all out in paraffin wax. And it all came together very nicely. And that's it. And it all works and it's here. Except that I can actually connect to it. So I would love to fly it around otherwise. Anyways, any questions?
Does using the Raspberry Pi on board, I mean, that has to limit the size of your, like a minimum size of your copter then, right?
Yes, it does. Yeah, it'd be hard to fit it on a regular frame because they're just not designed to take something like that.
Do you have any, I guess, issues with that, or have you made it smaller?
Not with the custom frame, because I designed it around that.
Sure.
So, yeah.
Okay.
You mentioned racing a couple times. I can't really picture what's the racing aspect of it.
No, just what it sounds like. We set up a track around a soccer field or a forest or something like that. There's usually a prescribed route. Last year when I'm the organizer in Madison, and last year we didn't really have any kind of time lapse or lap counting or anything like that. We are getting that this year. And it's kind of become a big event. It's all over YouTube, and ESPN's actually funding a big drone racing league coming up here. So
you're sitting at your laptop with a joystick and watching.
Yeah, generally these days it doesn't need a laptop or anything. It's kind of just goggles that take the analog signal, and then they're using just the old-fashioned controller like this. And like I said, those guys know how to work this, and they're very impressive using it. I'm not nearly that good, but they are. And so, like I said, but I just like the joystick as a better interface, and I would prefer digital video if we can work out the issues with it.
Are there restrictions in the drone racing league for like how you build your quadcopter?
Usually, size restrictions is the main thing. So the one I have here, excuse me, this is 250, and that's 250 millimeters. Measured from diagonal motors. And beyond that, there tends not to be too much regulation.
Okay.
Generally for indoor use, you might see 80 to 180 millimeters. That's kind of been a big thing of late, is how small can you go and fly them indoors. Which, mind you, also bypasses all FAA regulations. But otherwise, there tends to be just sizes, and I think as it matures, there'll be more regulations about motor size and batteries and such. But at this point, it's a little loose in that way.
Okay.
Do you tweak Perl in any way to kind of maximize?
Not really. No, I don't think I even did anything to the Raspberry Pi to for anything that direction either. I think the Wi-Fi and the camera interface are probably the limitations on latency more than Perl. Because the Perl aspect of it is really just taking data in one end and spewing it back out. Anything that has to do with encoding, that's all done in the C libraries anyway. So that is not actually a huge contributor to latency at all.
So how fast can you fly? How high can you fly? Can you fly high enough that you get out of Wi-Fi range?
Oh, easily. FAA regulations limit you to 400 feet. If you look on YouTube, there will be plenty of people who blow that limitation. I don't endorse that. Um, I don't like swacking that particular beehive. But I'm not sure how far you can get these 250s, to be honest. It's never been something I've been interested in doing. I think it's just showing off. Speed-wise, they can get very fast. 60 miles an hour is generally the standard that we tell people. I don't think this one would get that fast. Maybe this would be 30 or 40 miles an hour. But some of the higher level racers are pushing 100.
And how long can you fly? How much battery have you got?
About 5 minutes. I'd like to see an endurance racer open up, but that's probably down the ways for battery technology.
Looks like Jay might have a question.
Oh.
Oh yeah, can you hear me? I don't know if this is working or not. Can you hear me? Can you hear me? No? Anything? Hello?
Can you just put it in the chat over here? That might be the best.
Oh, text? I don't have a keyboard.
There we go.
Oh, you hear me now?
Are your speakers on, Tim?
No, I can hear from there, though.
Okay. Can you mute yourself up there?
You can hear me?
Yeah.
Oh, I'm sorry.
See if I can find it.
Just a second. Wait for Tim to mute.
So do speak or don't speak? You can't hear me?
Go ahead, Jay.
Oh, really? Is this working now?
Yeah, I just need to mute myself. But yeah, you're good.
Oh, cool. I get this. Thanks. Yeah, I'm Jay from Omaha. So thank you so much for putting this on the internet. I was talking to a friend of mine who works for NASCAR audio-visual group, and he was like, well, why are you guys not using Wi-Fi? Because we've got 4 cameras on 20 cars simultaneously, and everybody can see it all at the same time. And I said, I don't know. Is it because the power that you'd need for the transmitters is too heavy for the copters, or what? And I was just curious if you knew the answer. Why can't we live cast the way NASCAR can?
Okay, totally can. It's feeding into all the problems I kind of laid out here is how do you do it latency free? Well, you don't necessarily need that for spectators, mind you. But then you also get into weight issues. For NASCAR, you can get cameras with Wi-Fi down to 100 grams. On a NASCAR, that's nothing. I mean, yeah, they like to shave off every gram they can, but if everybody's hit with this 100-gram limitation, that's not a big deal. On a quadcopter, 100 grams is a lot. And so if you've got a camera that's broadcasting Wi-Fi that weighs that much, that's a fairly significant disadvantage there. So I think if to go that route, I think it would have to be the same camera that everybody is looking through. It can't just be a separate camera just for spectators. And actually, one of the things we are doing, I'm going to be at the Madison Mini Maker Fair doing drone racing. And one of the things we're doing there is to get 4 of the analog receivers feeding into a composite video switcher. We're going to put that up on the TV, and then we can switch between all 4 racers as they go. And that could also be used for recording or even sending video out to the internet. But the bad part of that is, again, that the analog video on this looks terrible. it's not something you really want to look at. It's not HD at all. It is good enough to see the obstacles coming your way, and that's it. So at this point, that's kind of the weight limitations there. So yeah.
Yeah, I race an immersion RC Vortex, so that works pretty well. But
You're
my NASCAR, I'm surprised.
using Perl basically to translate movements from your joystick to a bridge that's then translated to the flight controller, correct?
Right.
Could you theoretically use the same kind of thing to, I guess, program it instead of a joystick, just program commands into it to kind of like set up a set flight path and just.
Yes, a lot of the flight controllers with GPS modules do have waypoints that way. So you could say, take off, go to this waypoint, and come back, and the flight controller will do that on its own. But you could still use Perl to set those waypoints that way. Okay. Or you could use Perl to, combined with some kind of image recognition, which GStreamer does have OpenCV plugins, which can do some image recognition that way. So if you had Perl doing the image recognition and trying to navigate its way around an environment, that could be a completely autonomous drone using Perl.
How consistent would like you could theoretically like program it also to just do like tricks or flips or whatever, but I mean how consistent would that be if you just ran it like you programmed it to do like a flip or whatever like 10 times, would it do like a flip or would it just kind of depend on like various
I mean the AR drone, I think when you was talking about the pre-programmed flips, I see no reason you couldn't do that same sort of thing. I know on the AR drone, what it does is put a little throttle into it, so it's starting to rise a little bit as it does the flip, and then goes over, and then just kind of levels off and goes back because it has an ultrasonic sensor that can keep its altitude. It senses where it was before and then brings itself back to that point. So there's really no reason you couldn't do that in Perl. I didn't talk about the different modes in this talk. There is self-leveling mode, and then there's acro mode. And there's a bunch of others, but they all kind of fit into one of those buckets. Self-leveling mode, if you press it forward to go forward, and then released it, it would level off again. In acro mode, you press forward, and it keeps going forward until you manually bring it back. And acro mode is really easy to do those flips in. So the air drone, I believe what it's doing is putting it briefly into acro mode where it can just pitch a lot, just lots of throttle, pitch a lot, bring it back, levels out, and then it puts itself back into self-leveling mode. So that's the sort of thing you could do in Perl as well. I see no reason why you couldn't. You would just have to work out some of the details to make it do it consistently.
So you built all this software yourself. What are some of the alternatives instead of doing this all from scratch? Are there any popular other drivers that would be a good choice?
Quadcopter was the one that was out there when I started all this, and that's just for the AR drone. I was actually very happy about that because Parrot has very bad documentation. They like to think that they're a big open source company and helps people build all this stuff, but their documentation is very incomplete and often not worth completing. And sometimes just plain wrong. So Quadcopter is what I used a lot of the times to verify that I was doing the right thing for my implementation, and that helped a lot in getting things going. But Quadcopter is also stuck on the AR drone as far as I know. Maybe they've worked it out with the new Bebop, which is the new Parrot one, which apparently they had a whole bunch of problems with that one as well. Basically flying away and never coming back. It's a very expensive thing to lose like that. So I don't know where Quadcopter is at this point, to be honest, and I haven't really looked at other languages and how they've worked out their libraries, to be honest. I really should look at the competition, but you know.
Is there anyone else helping you work on this? Any bug reports or anything?
I get bug reports every once in a while. Okay. I had somebody help me out with the Mac implementation. There was, I think the original implementation used, what's it called? UDB broadcasting? No, multicast. That's it. The AR drone has a multicast mode, and that's the mode it uses by default. Max, it turned out, should work with multicast, but however it was doing it just didn't work, and the easiest way around that was just to use unicast. And so we worked that out with somebody else. It was like, hey, it's working now, yay. Okay, great. So I made a new release and was all working on Max then. And I get bug reports every once in a while. But one thing or another, I had one guy who wanted to work with the Bebop, that other Parrot model. And I said, oh, great, yes, please, help. And then he looked a little ways into it, says, they have no documentation. Where is all this stuff? It's like, yeah, and I never heard from him again, and I'm not really surprised.
Yeah.
Yeah, at this point, it's been kind of just me.
Okay.
When it loses, connection, can it, do a safe landing or do you return and come back?
Depends on how it's set up. With the AR drone, the one thing I'll say for the AR drone, it's a very safe consumer product. Once it loses connection, it just kind of stays where it is. And eventually it'll just kind of lose battery power and slowly come down. I think it actually auto lands at a certain point of the battery power. For these custom quadcopters, though, no, they will easily fly away. You have to explicitly program that in, and that's not something I've done. So yeah.
You said you had some thoughts on using any events, or you would rather not use that?
I would rather not.
What would you? I guess what did you like about it, or what would you maybe do?
I don't like the author. That's the main thing. Also, its interface is inside out, and it's a little clumsy to use that way. The author is very, very smart. We'll give him that. But I'll leave it up to you to look into him.
Yeah.
I don't want to say too much here. I don't like bad-mouthing people.
No, yeah, if you say that, it's kind of clunky, kind of weird to use. Like, what would you maybe have done? Like, is there any?
I've looked a little bit at I/O async at this point. I don't know if that would be suitable. Otherwise, most of the stuff in here would work just fine with a custom event loop.
Okay.
Cool. You guys good?
All right.
You want to mute yourself? I just sign off.
Okay.
All right. Thanks so much, Tim, for joining us. Really appreciate the drive all the way into Milwaukee and bringing your show for us. Let's see. Next month, we should have in person Doug Bell from Chicago, or Pre-Action, will be in town to give a talk. So look forward to that as well. And this video will be online if you want to watch it again later from the City Mongers meetup page. So check it out there. So thanks again, Tim. And we're signing off now. Thanks so much.